Okay, so I'm Sayan Mukherjee, and I'm here at the MPI MIS and also the University of Leipzig, the AI Institute hereby. I came here in May, and two people that I recruited to be here for at least some of the time is Erica Roldan and Andrea Agassi. And they'll also talk about what they want to do here and bring to the MIS. For me, it's really bringing in the mathematics of data science, which has not been traditionally part of math in the sciences. Historically, math in the sciences has been more physics, applications in chemistry, some in biology and things like that, but things like data science, statistics, machine learning have not been a core part of math and the natural sciences, and that's what I really hope to bring. And I don't self-identify as a mathematician. I do a lot of math, but I'm not. I'm a statistician. That's what I self-identify as, which is something that Germany does not have a really strong tradition of an independent core in statistics. And again, that's something that I want to build up and bring here. And maybe Erica, I really wanted to have you here because I wanted someone who was doing random topology and applications of topology and geometry, and also because of the outreach things that you bring. And for Andrea, really thinking about dynamical systems, probability, and bringing that entire aspect to the table. And I'll let you guys talk a little bit about yourself.
Okay, yeah, so what can I add? So you already introduced me as so someone who likes theory. As you, I'm not really a mathematician at the origin. Kind of grew into that profile, but at the origin I'm a physicist. And so what I'm hoping to do is to help in this direction of developing a kind of a sound mathematical description of data science and machine learning more specifically, like it has been done, of course. I'm not sure that I personally will do it, but I can help maybe the same way it has been done in quantum mechanics, for instance, in the last century. So I would be very excited to help a little bit at the interface between probability theory, analysis, and data science or machine learning to develop a little bit our theoretical understanding of these models, such as neural networks that are really, not very well understood for the moment.
Yeah, well, thanks for the introduction, Cheyenne, and I'm very happy to be here at the Max Planck Institute for the mathematics in the sciences. And my field is, as you mentioned, is stochastic topology and its applications, and it's well known to have a strong application in data science with topological and geometric data analysis and other applied computational topological frameworks. And in particular, I think we're very excited to bring together also percolation models and other physics models in physics with the understanding of the topology and the geometry in these stochastic processes. So, and I'm very excited. The team is building in a very inclusive and diverse way as well. I find that is it's encouraging people from a lot of different backgrounds, and this will make the research groups very strong.
Yeah. For me, with my kind of new position, it's very different than what I was in a way at Duke, because it's much more. I have many more resources. There are more expectations. You're much more. You're much less just the faculty member, right? And in a way, it's exciting. I can reinvent myself, and I'm trying to do things, including engineering things, building holograms and things like that I would never have thought about trying to do there. And one thing I really hope is to make Leipzig between the this institute and the AI Institute one of the kind of world leaders in more theoretical data science and theory of machine learning. And again, that's something that I really hope we can do and push through.
Yeah, I think, I mean, given the location and the collaboration between closedness, let's say, between SCADS, this AI Institute, and the university and the MPI, I think the potential is very strong. So thank you.
Yes, I agree. And what you're mentioning, I think we are, in a way, daring to erase the boundaries between statistics, engineering, mathematics, and yes, this. I think there is a very strong movement in Europe for good science that could be a risk taken, but that is high reward in terms of the outcomes. And I think this is what is possible when you have different aspects of mathematics and also engineering and data science and AI and machine learning. So, yes.
I think it's also a really good time to try to do this because the engineering aspects of neural networks and machine learning and data science and the computing aspects have really exploded. And the fundamental understanding of them has not, right? And I think that's something that we can, I think, kind of really contribute to. And the idea, I think, is also, for me, is replicating the classic structure of a statistics department or a statistics unit as you would have in, for better or worse term, Anglo-Saxon places like England or the US or Canada. It doesn't kind of make sense here, right? So here to really drive that through with math, right, and make it integrative. And it's a great opportunity because given the strengths of the other directors and what they're really good at, integrates really well with in my view, right, with building that theory of data science. I think classically here at a math institute, right, at this math institute, you have the analysts, you have the algebraists, you have the geometers, right? And in some sense, I think we all do a little bit of all of this, right? Because my goal is not to solve a problem in analysis. My goal is to understand math and data science, and to do that, you really need all these tools. What scientists have been inspiration for you and why? And I'm going to go last, so either one of you guys can go first.
Sure, so I can start. I think during my development as a scientist, I was fortunate to have a few good supervisors. I mean, all of them were good supervisors. I had a few people that follow me, and I think I learned a lot of things from them. I should probably name them. So Jean-Michel Graff was my master thesis supervisor, then Jean-Pierre Ekman and Amir Dembo as both PhD supervisors, and then Jonathan Mattingly and Sayan also during my postdoc. And I think I learned a lot of things from diverse and different things from every one of these people. And maybe as a further person for me, I think, coming from physics, surely Albert Einstein and Emil Noether were some very important role models in, someone who has really deeply changed science and created really bridges between topics and between disciplines that were not really talking to each other. So I hope that would be something I would hope to do one day.
Well, I guess if I can make my story briefly and how I got inspired to do mathematics because of an outreach book. I was actually out of school and it was going to be forever. So I think the role models came from books, and then after that I found my space and I found inspiration in the mathematical community in general. And for jumping to my PhD, coming from Mexico, I was very, very lucky to have Matthew Kale as my advisor. And then I went to Ohio State. And yes, I think with respect to people that is alive and that have made a strong impact in my life, I think the women in computational topology community is a very strong community that allows us to navigate the difficulties of being a non-cis male in the environment of academia. And yes, and now I'm looking forward to keep growing. And I guess Mary Somerville is my role model that was during my undergraduate period. And yes.
I guess for me, there are, I guess, three people. I was thinking about this for a little bit, and one is Alan Turing, because he did so many things, right? And he was really, really an exceptional individual. And there's a really, really cool story. There's one of the people I worked with at when I was a postdoc at the Broad Institute. His name is Nick Patterson. And his first job out of grad school was at whatever the follow-up was to Bletchley Park. And Nick told me the story, which was amazing, that there's an entire formulation of Bayesian statistics that Alan Turing did before people even knew about it. Exact same ideas, different words. And one of the people who worked with Alan Turing was named I.J. Good. And I.J. Good published a paper on a species counting model. And that model actually had nothing to do with species. It was all about code breaking. But he couldn't publish it as a code breaking, right? So there's that work from code breaking, there's the Turing test, it's just, and he was one of the people who really formulated the core mathematical ideas, starting in AI even, right? So that's again, Alan Turing is amazing. For me, another person is Sewell Wright, who is really formally a biologist, but did the first work in graphical models, did a lot of initial work in causal inference, was just a brilliant geneticist, right? And there's an amazing picture of Sewell Wright holding a guinea pig, because he worked with guinea pigs, and using it as an eraser, right? This is just beautiful ideas of like how math is so fundamental to genetics, right? And unlike a lot of the founders, like people like, Ronald Fisher, Sewell Wright was actually a really decent person, right? So Sewell Wright is another one. And the last I would say is, again, Emmy Noether. This idea of really formalizing topology and showing that it's algebraic, and this idea of thinking about matrices as abstract objects, right, is just really just an exceptional breakthrough, right? So those are three names that I would have. So let's see. Okay, for me, challenges in terms of being a scientist. What I've always had a hard time is, I was never one thing, right? For example, even when I got the Alexander Humboldt professorship, it was like mathematician, statistician, computer scientist, right? So in some ways it's great because you get to interact with all of these, but in other ways, it sometimes is just so frustrating because you go to different places and say, oh, is this really core math? Is this core CS? Is this core statistics? So for me, I think a real challenge has been, how do I work within these different fields, kind of blend them, right? And still manage to show people who are in the core disciplines that I'm really one of them. I think that's, for me, has always been a challenge.
I fully agree. I mean, having grown as a physicist and coming to math, of course, it's probably even, less than your struggle, but it's still hard to participate to, say, conferences or, social events where there are two sides and you feel you might belong to either of them, but none of them recognizes you as one of them. But on the other side, if you accept this kind of how should I say, if you accept this kind of discomfort in a way, then it can also, I think it pays off. I think, I don't remember the name of the person who wrote this, but that in my case, mathematical physics is really so your job is really there is a physicist who has a certain line of research, there is a mathematician who has an orthogonal line of research kind of, and develops tools that don't really talk to each other, and you want to make that connection. And I think, if people start to see you as that person, then you can bring a lot to science, even though, as some may say, I say about myself, I don't really understand neither of these 2 points, but you can still give a contribution to science by bringing them together, and I think that's a great.
Yeah, I think for me it's within mathematics that I experienced this like not knowing how to label oneself, but I kind of enjoy it. The things that I work with is probability, combinatorics very strongly, and then computations are part of my research to be able to make conjectures, and then touching physics. And yes, I think it's great, but also it's difficult to make community in each one of these niche, right? But I enjoy it, and I think one of the other areas that I do research is in educational technology and learning analytics, and that has been very rewarding with respect to bringing to my teaching and outreach, like applying theory that is being developed with respect to collaborative and learning by teaching. And so I think this other part of educational research also has paid off.
I think another thing I would like to add is also, I think, at least for me, it's hard to find the balance between your kind of 2 missions, which is one is the one of educating people and transferring what you know to other people that could do a lot, and doing research, so like kind of more focused effort to push forward in the research and the amount of knowledge the humankind has, and balancing between these 2 is I think is something you did very well, and also between the management of a group, and at the same time one has a finite amount of time, let's say, and we have to handle it carefully. And I think many scientists, because there is another question, which is what do you suggest young scientists? What do you think? What would be your advice to young scientists?
I think
that could point in that direction.
I think young scientists, I think it's important to not always just do whatever is the hottest thing, right? Do things that kind of genuinely interest you, and always learn stuff and always think about new things. I mean, when I started at Duke, I got the job because I did a lot of applied computational biology, right? I mean, I also was doing theory, but really the reason I got the job was because I could do computational biology. And then I started doing that. I did more theory. There were some people there that were starting to do computational topology. I didn't know much topology. I learned topology, and I ended up doing a lot of the basic stochastic topology work, right, and applied topology, right? So I think there's this idea that you can always learn. You can always, do new things, and you should do things that you find interesting, and or are really useful and important, right? And talk to people. Talk to various people, and think about, what you might want to do.
Right.
So.
And if you can, I think a message. So I remember once asking to a director in an institute in Switzerland what was their advice on my career. Where should I choose? How should I choose where to go next for a PhD or something like that? And the answer was, I give you two pieces of advice. Do something that you feel excited about, and do it in a place you feel excited to do that in a group where you feel included, in a group where you feel, there is something going on. And again, I think, what's happening here is pointing very much in that direction for both of these things.
Yeah, I guess I would like to perhaps address the community that it's not necessarily like already in these circles of science, like for underdeveloping countries. And I think it's important to reach out to people. And if you're reading a paper from someone, and you want to ask the question, just write to this person, and do not get discouraged if you don't get an answer. And yes, I think it's important to, as you are saying, Sayan, like try to reach to the people who is doing the kind of science that inspire you, and then yeah.
Yeah, I think one version of this is, when you are more junior in science and building things up, there's a lot of often worry and concern about, where should I publish? How many papers do I need? What do I need to do? And all of that. And there are practical reasons why people can, but I think a way of simplifying all of that are, who are the people in areas that I respect, right? And do I think that they respect me, right? And I think that that's, if you can do that, if you can get there, right? I think that should be really the goal, right? Rather than necessarily worrying about all of these other details. Because, yeah, so there's this, I think for all of us, there's a beauty in math, right? And I think all of us, part of that beauty is in randomness, right? And I sometimes find it kind of really hard to explain to people why randomness is so, so exciting and so interesting and so just fascinating. And there are two versions of this, and I think they'll touch on both of things that you're interested in. So one version of it is just there's this beautiful connection between randomness coming from statistical physics and dynamical systems and notions of entropy. And these are just amazingly beautiful and deep ideas that touch so many areas, so many fields, so many ways we think about the world, and are actually also fundamental in data science now. And some of the real breakthroughs in the math of data science is at that interface of using tools from statistical physics, thinking about algorithms as dynamical systems to really kind of break through, right? Another version of this is really thinking about geometry and topology randomly, right? So classically, people, and this was also true in biology, so before Darwin, right? If you look at Linnaean perspectives, people really looked at Platonic ideals. And you had the same words in geometry, and in biology you had the genuses, right? And these were ideals. There was like an ideal duck. There was an ideal, and what Darwin really realized in a real breakthrough, because he cared so much about evolution, is we care about variation. We care about variation of shape. We care about variation in form, right? So this idea of taking traditional topology and applying it to random stochastic models is, for me, just so exciting, right? And I think there's just so much open in that. And so, yeah, so that's...
Yeah, I guess the power of being able to escape the deterministic tools that we have is, it's indeed what makes the probabilistic method now applied to topology, as you're saying, and geometry. So, yeah, I agree.
Yeah, no, I'm very excited about all you said, and again, I map it back to what I know. But I remember the first time I came in contact with the ideas of statistical physics, I was flabbergasted. It was just wow. So you take a lot of complicated things that are very hard to describe. You zoom out, and everything becomes one equation, one thing, simple or not, because then Navier-Stokes,
Not the easiest. But
not the easiest, but definitely simpler than the basic object you were looking at. And I'm fascinated by two aspects here. The fact that mathematics can allow you to understand and describe this is magic, in my opinion. There is no reason why this. Of course, that's a very personal conviction, but I mean, I'm always surprised by the fact that mathematics can describe all this so nicely and so perfectly, and feeding back into it. So giving tools to statistical physics, and the two really talk. It's not just mathematics giving something to physics or to our understanding of reality, but also our understanding of reality will guide us in discovering new math, right? Mm-hmm. And I think this is exactly, I mean, in the case of randomness, but more generally what you were saying, right? We can take the tools from these two disciplines, feed them into data science, and data science is already giving back by giving new theorems, giving new insights in this new abstract and wonderful language that is mathematics.
Yeah. So you mentioned Navier-Stokes. So there's this one question, I guess, very classic in math. What are your favorite millennial problems, or what are your favorite math problems, right? And I think for me, I've never had one. And I think a lot of that was because my goal wasn't to solve some theorem or something that no one has solved for so long. There was one exception. I tried to prove something about Cheeger inequality in middle dimensions, which turns out is really hard, and we made some success. Many people have tried and failed, and Jorgen's made some progress, but But the reason I looked at it was actually I started with a data science question. So it's never for me been these are open, hard math problems. It's really been, there are things in data science, statistics, machine learning, or something, and I want to understand them better. And then you sometimes dig into the math to do it, right? For example, one of the things we recently worked out was a sheaf theoretic characterization of shape space, right? And what was exciting for me about that is using math that's pretty sophisticated, right? For something that started as a really applied problem, right? So that's kind of been my take, right, in terms of, these big open problems.
I think the problems I've been trying to solve since my PhD research agenda has been definitely problems that I fell in love with them, and I don't think they were already known problems or posed problems, but then it gave me the opportunity to bring to models like first pass percolation model or percolation clusters, this idea of understanding the topology and the geometry related to the topology. And yes, I think with respect to bringing new insight to bridging two different areas of mathematics, that was very exciting. So I've taken the risk sometimes to dare to understand different questions in areas such like probability models and with the lenses of topology. I think this is one of the most rewarding feelings that I have. So, yeah.
So, I guess one thing people sometimes ask are, what have been important steps or achievements in one's career? So, I mean, for me, I started graduate school at MIT for my PhD, and I was initially, my advisor wanted me to do computational neuroscience, which turns out is something that I just deeply disliked. And so I ended up doing very theoretical machine learning and probability theory and empirical process theory because I liked it. And I think that was, it turned out really, really helpful for me, right? Because it gave me a really good basis for what I did for the rest of my career in terms of being able to do machine learning, statistics, probability, and kind of form that foundation. And then I did a postdoc at the Broad Institute where I started learning some biology and genetics. And there's no way, well, there's no way I would be mistaken for a biologist. My wife and brother are biologists. But really seeing that and seeing people doing that science and seeing applications, again, I think was really, really transformative. And then I was very lucky, I think, that I ended up choosing Duke because the collaborators and the way I was able to develop my career there and the interdisciplinary environment was really, really amazing. And taking this chance of coming here to Germany to build up a, this interface between math and AI is now a real adventure, and I'm really kind of excited by it. So those are for me some of the kind of key, choices. So yeah.
Yeah, I mean, I think what I would say is very similar to what you just said, but just to rephrase it slightly. I mean, I think in a way I remember, I think 2 days during my PhD, which is one is the day when I decided I would do it, and I would be stubborn, and despite the relatively hard time, of course, I would just go ahead and finish this. And the other is when I understood that if I liked something, that was a good enough reason to push forward, if I believed in something and liked something, to push forward and do it, like you said. And I think the other thing I would say, but also you have already said, is I learned coming at Duke, that was also an important stepping stone for me, because I learned the importance of a diverse and communicative environment in a department. And I really think this gives a lot to a university, and I think, or to a research institute, and I think I think it's an objective one should strive to, as an institution.
I think I remember what was the change point in my career was when I went to the topology in motion semester at ISERM. That actually we met there.
Yeah, I was one of the organizers.
Yes, exactly. And I think being there during my PhD, these 4 months of talking with people in the area and doing research and collaboration and just taking the blackboards and not having any other duties, but just talking about mathematics and in particular the area of stochastic topology, TGDA, and related topics. I think that is when I decided, okay, I want to be research focused in my career. Also, I love teaching and outreach, but I realized this is what I want to do. So I think the international network that is giving these kind of workshops in different institutes of research, it's a very important for spreading areas and for bringing young scientists into these areas. Yes.
I guess maybe one closing-ish comment that I would have is I'm really happy and excited that the Max Planck Society and one of the top math institutes in the world thought that it's really important to have someone that's a statistician, and really including that part of math, right? And that does not always happen, right? And understanding how important data science and statistics in these areas are as a fundamental part of mathematics is really, for me, really exciting.